Hello, chemistry students. This is Sean McMahon, your professor. Last time we talked about chapter 3 in lecture 1, matter. This lecture, lecture 2, will be focusing on the second portion of the actual chapter, which is energy and its types of calculations. But just as a quick review, last time we classified matter. Matter is anything that takes up space or occupies volume. We can categorize that into pure substances that have fixed proportions and fixed ratios. So that basically means they're made up of one type of atom or molecule. And then we had mixtures with variable compositions that are not connected per se chemically, through bonds or not united. So an example is we have the element. Element is the plural for the singular of an atom. So you can think of, if I had a bunch of copper atoms lined up, I would have this copper bar, which is a pure substance. Okay, it's a fixed proportion. It's basically the simplest formula would just be Cu for cupron. Compounds, on the other hand, they can have one or two or more types of atom, but they are chemically bounded so that they have a fixed ratio. So compound is the plural form for the singular of a molecule. So again, pure substances, you can think of atoms and molecules. And we talked about this last lecture. Mixtures, we can have variable proportions. A homogeneous mixture, homo just think same throughout. So like this structure here, or this mixture here is tea, and it has different components. For example, caffeine, it has the sucrose, it has water, but they're in variable proportions. I could put more sugar in here and keep adding sugar. The reason why I can add variable proportions is these are not chemically bound to the water molecules. Heterogeneous typically means different, so there's a separation. That has to do with how they interact with one another. So we can see that the oil likes to interact with itself and keep separate from the water, creating this interface. But again, if you need to review that, that was lecture 1 of chapter 3, when we talked about matter. We also talked about the states of matter and how we observe physical and chemical changes. Now, the reason why I'm reviewing this is a physical change would just be a change, let's say, in the state of matter. So here I could have liquid butane, and then I could release the pressure valve and it could vaporize into a gas. So whether it is a liquid or a gas, it's still butane. It has the same chemical makeup, okay? So it's 4 carbon and 10 hydrogen. So it still has that fixed proportion ratio. However, a chemical change is where now I actually kind of break the bonds in the butane and move the atoms around and reshuffle them to make new compounds. So that's CO2 and water. So in combustion, when I burn the butane, I have new products, but I still have the same amount of atoms, and I just move them around and bind them differently. So they have a different composition now. That's how I know it's not just a physical change, it's a chemical change, because there's different combinations, different bonds. And we talked about this last time. Is this an example of a physical or chemical change? Copper metal forming a blue solution when dropped in nitric acid. It's chemical. Evidence of the reaction is a color change. A train flattening a penny. Well, that's just a physical change. It's still a penny. I'm just squeezing it down. A match igniting a firework. There's a release of heat, energy, and light. That's why they're so beautiful. So that's a chemical change. Ice melting into liquid water. Ice is H2O, just in a solid state, so the particles are fixed. When I provide energy, those particles separate a little bit, and when they separate, I have what's called a change of state, and now the particles can slip and slide. There's more freedom of motion because there was that energy required to separate them, but now I'm in a different state as a result. Physical change. So this brings us to today's lecture. So now that we're talking about matter and its changes, we need to understand that we can also have what are called energy changes that are accompanying those physical and chemical changes. So the first thing is the law of conservation of mass. As I said with the example of the butane, I can't create new carbon atoms and hydrogen atoms out of thin air. All I can do is break bonds, rearrange the atoms, and form new bonds and new pure substances. So there is no new matter because it's not created or destroyed. Okay, so that's the law of conservation of mass. The mass stays the same. So if I took that butane and that oxygen, and I initially weigh, because the oxygen had to combine with the butane in the combustion reaction, if I weighed each component, I would get a certain mass. After the reaction, if I actually collected the CO2 and the water that vaporized from this burning, it would still weigh the same. Now, there'd be different masses for each species because there are different formulas and different ratios, right? So this was C4H10, this is O2, and this is CO2 and H2O. So you basically have different ratios. Now, I would have to balance this, but for the most part, just realize I'm going to have the same number of carbon atoms on both sides, so the mass isn't going to change, the same number of hydrogens and oxygens. I'm not going to really balance this because that's a later chapter. We're going to get to it. This is just showing you that I can't create or destroy matter. I can merely move it around. So when we burn butane, again, a lot of that is for the release of that energy. So we should talk a little bit about energy. And even though chemistry is a study of matter, energy is going to affect matter in some form or another. So what is energy? It's anything that has the capacity to do work. Well, what do I mean by work? Work is where you have a force and it acts over a certain distance. So basically, work is force times distance. If you've taken any type of physics, it's a Newton meter, and we'll be converting Newton meter, which is essentially a joule of energy. And we'll talk about that, that unit for energy. And what I mean by unit, so for length, there's the unit of inches, which again is within our English system, or there could be the unit for length in centimeters, which is the metric system. So joule, right, is just a unit for energy. Now, how can we understand what I mean by work? Well, this man is applying a force on this box, and that would be the force component. And if he moves it over a certain distance, that would require work. And this makes sense. It requires work for you to move something heavy. So that is a form of energy. You have to use energy to do the work. Another form of energy that we'll be talking about is heat. And heat essentially flows based on differences in energy. And this makes sense because typically heat flows high to low. It's kind of like diffusion, right? When we think of diffusion, it's from a high concentration to a low. It's the same with heat. You may have heard that heat rises, right? In the house, well, why is that? Well, hotter air, for example, is moving faster. So if there's slower moving particles and there's more space, it's going to move in there and rise. So heat flows typically from hotter temperatures, okay, or more thermal energy to lower temperatures or less thermal energy. So what we need to understand is energy, whether it be work or heat, is essentially an exchange through contact. So how is that? Well, this man is contacting this box and exchanging his work to the box to move it. Well, what about the heat in air? Well, through collision. So when these particles are moving faster and they collide into other particles, now those particles move faster, and now they, because they're moving faster, they get hotter or they have more heat. Okay, so you can think of it through collisions. All right. So energy, heat, and work. You can think of energy as a quantity that an object has, right? And you can think of it as, okay, there's two different ways that I can either absorb or release energy, either through heat or work. Okay. So basically, I can exchange energy with other objects, either it coming into me or it coming out of me. Okay. Another way of looking at it is, okay, well, heat, work, are there other forms of energy? Well, there's electrical, there's solar, there's many forms. What we want to really focus on is kinetic energy. Short for kinetic energy is KE, and this is usually associated with motion. Okay, it's not a requirement for this course, but you may have seen in other courses they write kinetic energy equals 1/2 mv squared. The V stands for velocity, which means speed. So speed squared, and then the M stands for mass. Very similar to Einstein's E equals mc squared, where mass, where M is still the mass, and then the c squared is the speed of light. So V is velocity, it's speed. So the more mass something has, if it's moving, the more kinetic energy. But what's even more important is the faster it travels, the more kinetic energy. And that explains why, let's say in football, you could have a smaller person, but if they're moving faster, they have more kinetic energy and they can knock over a larger football player. Another form of energy that we need to consider other than associated with movement, kinetic energy, is potential energy. And that's typically associated with its position. So some of you may have seen potential energy with, mgh, where m, again, is mass, g is gravity or acceleration, and then h is a distance, okay? So potential energy is based on position. So the total energy that an object has is both kinetic and potential energy. So you have some kinetic energy, movement, right? And then you have some stored energy, right? Because potential energy, it's with its position and it's stored. It wants to move, but it hasn't quite yet. And we'll talk about how we store that energy. So with potential energy, we're basically saving it so that later we can maybe do some work or create some heat. When we think of homeostasis, right? We consume fuel, food, which is a form of potential energy, so that we can do work with our body, but at the same time, have thermal regulation with our body temperature, because we have to maintain a certain body temperature. So that's a form of heat as well. So how can you recognize whether or not something has potential energy? Okay, so let's take a look. Water behind a dam. This water has potential energy because it's stored, because really water wants to roll downhill and move, right? Movement, motion, kinetic energy. But if I'm blocking it so that it goes through turbines to turn those turbines to create electrical energy, we can't create energy, we can only transform it, then I'm storing that potential energy for the normal thing for water to roll downhill. Another example, a compressed spring, right? So if we compress a spring, it has potential energy stored in it. Once I release it, right, it might open up and move, kinetic energy. Really what we're looking at is chemical bonds in food. So you may have heard of adenosine triphosphate. ATP is a form of stored energy. Well, that's true. We have energy in bonds, okay? So when those bonds break or form, that energy that's stored in the bonds can either be released or absorbed, right? So kinetic energy is associated with movement. Any object moving has kinetic energy. So water flowing over the dam is kinetic energy. So that's why we store it, so then we can control it when it flows and harness its natural, form of kinetic energy and transform it into something different. If you swim, that's a form of kinetic energy, you're moving. If you work out, kinetic energy. If you're burning gasoline, right, that is going to cause movement, because the gasoline is going to change into CO2 and H2O, and they're going to be moving as well. So when we look at these examples, so this is sample exercise 4, if you have the handout, can we identify this as potential energy or kinetic. So someone rollerblading, is there stored energy or are they moving? They're moving. So this would be an example of kinetic energy. Peanut butter and jelly sandwich. So that's not necessarily moving, but stored in the chemical composition of those molecules is the energy in those bonds. So this would be an example of potential energy. Once we consume that food, we can then harness that energy to do other things. Mowing the lawn, well, that's kinetic energy. The gas that's in the gas tank. So if the lawnmower is just sitting there and it has gasoline that we can burn, right? But if we're not burning it, if the gas is just sitting there, what does it have? It has potential energy because it's got energy so that in the future we can go ahead and burn the gas so that we run the motor and have the lawnmower cut the weeds for us. Of course, you have to actually move it too, although now you can drive them, but so that's how you identify those. Kind of the big takeaway is we know energy can do work, but I want you to think of energy in terms of either kinetic, motion, or potential energy due to position. Now, why do I want to do that? Thermal energy, if there's any type of movement, there's going to be some type of, because heat transfers from one object to another, there's going to be a change in temperature. That's kinetic energy. So when you think of heat, that is an example of movement, because to heat something up, particles have to move faster. That's kinetic energy. So when we talk about science, we're looking in the form of kinetic energy really at heat primarily. Or for this class, I shouldn't say science, I should say for this chem course. Potential energy, I want you to think of what's referred to as chemical energy, and that's associated with the positions of electrons in the nuclei and the nucleus. So we haven't talked yet about atomic structure, we will be, but essentially all atoms have a nucleus. In the nucleus, you have your protons and neutrons. Protons have a positive charge, neutrons are neutral. So the positively charged protons are attracted to electrons. Electrons occupy, we'll simplify right now, different regions of space, okay? And they're attracted, like how magnets are attracted to each other, right? So the further away the electron is from what it's attracted to, the greater that position is, right? It's further apart. So what happens is there's more potential energy there because there's a greater distance. Now I know with magnets, at first, if they're really close, like if an electron's really close to the nucleus, it's harder to remove that electron, okay? As it gets farther, it's easier to remove the electron, but also there's more potential energy. When I break bonds, those are essentially electrons, right? Bonds are two electrons being shared or an electron transfer. So anytime I'm reshuffling atoms around, it's so that I can break bonds, form new ones. And that's just moving electrons around. And what happens is when they recombine, they're going to be in a different position with the new atoms that they're next to. So that's where the chemical energy comes from, stored energy in electrons. If we want to think it of a macro level, because what I was describing was kind of micro, within bonds, the positions of the electrons of the nucleus, we can think of it as a macro, right? So here we have a mass. It's a certain distance to the ground. The ground, Earth, has a gravitational force that it's attracted to that's pulling down on it. So right now, this has potential energy. What's the potential energy? Remember, I said mass times gravity times height. There's a height here, right? And that'll be in meters. Gravity is 9.8 meters per second squared. And then there's a mass. So the potential energy has a mass, and that's this weight here. If I push this over, okay, essentially, and that's a lot of times the potential energy to be converted to kinetic needs some type of catalyst. But what'll happen is it'll start moving and drop down to the ground. So at this moment in time, I've converted this much potential energy into movement kinetic energy, and there would still be this much potential energy. When I go all the way to the ground, all that potential energy based on this distance has been converted to kinetic energy. And if there is any difference left, once this object hits the ground, it's going to cause vibrational energy on the ground, and the ground will absorb it. And that vibrational energy causes it to get hotter. And it may be insignificant, but that's essentially a transfer of heat from one object to another, the ground, right? And it's transferring it through a collision. So just like mass, energy is conserved. I can't create or destroy that out of thin air. I can only transform it. So this had potential energy, and I transformed it into kinetic energy and heat. And typically you want to go to lower potential energies. So what's a lower potential energy? Well, if distance and position determines how much I have, the lowest potential energy would be all the way to the ground, which is referred to as the ground state, right? So when we talk about electrons, electrons get excited to higher levels of energy, and then they fall back down to the ground state to become more stable, okay? I'm moving into the future, but yeah. So energy can be changed from one form to another and then transferred. Now we're going to talk about different units. One of the units we use is joules, which is named after the English scientist James Joule. But basically what it's showing is energy is being conserved. And this was the apparatus he used. Now, there is conversion factors. So we had stated before, for example, for length, 1 inch in our system, right, the English system, is equal to 2.54 centimeters, okay? So it's the same length. I'm just moving the ruler over. And the reason why the numbers are different here, right? 1 is different than 2.54, even though it's the same length, is I have a different unit. Whoops, sorry about that. So it's the same thing here. We have calorie. 1 calorie is the 4.184 joules. This is a conversion factor you should get comfortable with. We use this when we start talking about water and things like that. That'll be the next lecture where we do what's called specific heat calculations. Basically, to raise 1 gram of water, let's say 1 degree Celsius, from 25 degrees to 26, it would require 1 calorie, which is equivalent to 4.184 joules. It's just a different unit. Same amount of energy, but a different number because a different unit. Now, we're familiar with calorie because we think of our diet and nutrition. What's a little tricky is, in our diet, this is called big C. So they write calorie with a capital C rather a lowercase. But the reason why I personally think this is tricky is big calorie is actually 1,000 calories. Or you really can think of it as 1 kilocalorie, right? When we're talking about little calories in the form of this course, right? So a lot of students say, well, why did they do that? That's confusing. Probably because, you know, when you flip over a Snickers bar, they didn't want people to think 250,000 calories. Oh my God, that's so much. So I actually don't know. Another unit is 1 kilowatt per hour is 3.60 times 10 to the 6 joules. This is one I don't expect students to memorize. We don't use this a lot in our chemistry course. This is almost more like a physics type thing. And you can think of this with SDG&E, right? Kilowatts per hour for your energy. Our focus is really going to be calories to joules. But when I talk about calories, we have to be able to distinguish between the caloric diet calorie. So this is the diet calorie, which is really the big C, which is 1,000 little c calories. So let's try to do a calculation here, right? So let's say I'm going to burn a match and it's releasing 512 calories of heat. So I'm given 512 calories. I want to know how many kilojoules, right? So in the previous slide, we saw that 1 calorie is 4.184 joules. So I can convert calories to joules, knowing that there's 1 calorie for 4.184 joules. But I need to go to kilojoules. How do I do that? That's where I use the metric system. Kilo means 1,000, right? So to get 1 kilojoule, I would need 1,000 joules. So you have to kind of use the metric system to go from joule to kilojoule. And we're using that energy conversion factor that we just talked about. And now we can set it up. And always we want to put the unit we're trying to cancel that we're working towards. We want to put this unit on the bottom of the conversion factor so that they cancel. But I don't want just joules. I want to go all the way to kilojoules. So there's 1,000 joules. Sometimes students can write it as 10 to the 3 because 10 to the third power is 1,000. That's totally fine. But that's going to cancel out my unit of joules. It's going to leave me with kilojoules. Now for significant figures, there's 3 sig figs in this number. So my final answer should have 3 significant figures and the unit of kilojoules. So it's 2.14 kilojoules. So we see that my final answer has the correct number, the correct sig figs, and the correct unit. Those are the 3 things I need. So that was sample exercise 5 if you have that handout. So we talked a little bit about heat being thermal energy. It's associated with motion. The faster the particles move, the greater the heat or thermal energy. And, you know, if you get cold, sometimes don't you kind of move your hands fast to warm them up? You can feel them getting hot. That's because when things move faster, they have more thermal energy, okay? So there's more heat stored. Why did I do that? I did this because I'm hungry. The peanut butter, the pizza. Okay, so basically, yeah, you put heat into the frozen pizza and it cooks. So that's a transfer of that heat from a higher source, the oven, to a cooler source, the frozen pizza. All right, so let's try another calculation with just the units of energy, where if I had a Butterfinger and it's 270 kilocalories and I want to metabolize this, how many joules would this give me? Okay, so I start with 270 kilocals. Now I can convert kilocal into calories. How? The metric system, okay? But I don't want to stop at calories. I want to go to joules. So how do I do that? I'm going to use that conversion factor that we just did, that 1 calorie is 4.184 joules. So how do I write this out? 270 kilocalories. Remember, I want to cancel out kilocalories. So that's going to go on the bottom. 1 kilocalorie is 1,000 calories. So that unit's canceled. And then from the previous slide, 1 calorie is 4.184 joules. Now that gives me a rather long answer. It's 1129680 joules. But I want to follow significant figures. So there's only 2 here. This is a trailing 0 without a decimal. So my final answer should only have 2 sig figs. So I have a choice. I can go 11, 0, because here's 1, 2. The 2 is less than 5. So I'm going to drop these and just put the zeros as placement holders. But if you don't want to use all the zeros, you can go 1, 2, 3, 4, 5, 6. 1.1 times 10 to the positive 6, because this number is bigger than 1, joules. And that's my final answer. So that's actually a lot of joules, right? What is that? That's 1.1 million joules to burn, you know, that Butterfinger off. That's a decent amount, right? Because it's 4.184 joules to raise 1 gram of water. And I know gram's small, but 1 gram of water, just 1 degree Celsius to heat it up. So that's a lot of joules, right? Magnitude wise. Well, now, some people use temperature and heat interchangeably, but they're really not the same. Heat has a unit of energy, which is joules, and we talk about the transfer of that heat energy, but we can measure that transfer of heat energy with temperature differences, okay? So cold ice, if it's dropped in water, right, the heat's going to transfer, and the water, right, is basically going to get colder, and the ice is going to release that heat there. So that's transfer of thermal energy. Temperature is just measuring the thermal energy of it and not really that transfer. So heat is the transfer of the thermal energy. Units will be joules. Temperature is measuring at that point of time the amount of thermal energy, and there's actually different temperature scales, okay? So in science, we're going to use Celsius. Now, here in the States, we use Fahrenheit. So we're, again, you know, one of 3 countries, but we're going to use Fahrenheit, right? Everywhere else, they use Celsius. And we're going to also see there's a Kelvin scale. So those are the 2 other scales. Now I'm showing boiling water and I'm showing where the thermometer is. But basically, what I wanted to show is a Fahrenheit degree is 1.8 times the size of a Celsius degree. What do I mean by that? So here's my Fahrenheit. Here's my degree Celsius, right? Water, its freezing point is 0 degrees Celsius, okay? For it to boil, I need to go to 100 degrees Celsius. So on the Celsius scale, that's a difference of 100 degrees. Now, we use Fahrenheit. The freezing point's 32 degrees Fahrenheit, but to boil it, it goes all the way up to 212. So that's a difference of 180. So there's a ratio of 180 to 100. So that means a Fahrenheit degree is 1.8 times the size of a Celsius. If I look for the Kelvin scale, water freezes at 273.15, but it boils at 373.15. So it is the same, basically, ratio. You can think of it as it's like 2 parallel lines, 2 linear equations that never intersect. They have the same rise over run, the same slopes, but they don't intersect because they have different starting points. Celsius is at 0 degrees Celsius, and this is at 273. Right? So this would be up here and this would be here, but it's 100 degrees. This has a different slope. So there's 180 degrees to 100. If I do that as a ratio, 180 divided by 100 is 9:5 ratio. That's how I learned it, 9/5, because we did a lot of fractions. If you prefer decimals, it's a 1.8 to 1 degree Celsius ratio. If I make the adjustment, right, from the Fahrenheit, which is 32 to degrees Celsius, I have to make an adjustment. There's a different starting point, and that's from 0 degrees Celsius to 32. So now, what does that mean? The rate of change from Celsius to Fahrenheit was 180 over 100, which became this 9/5. So I would have to times my Celsius by 9/5. And if I wanted to convert it to Fahrenheit, because Fahrenheit is 1.8 times faster, and then I would have to start at an intercept of 32, so I would have to add 32. Now, why am I doing that? You have to be able to convert from Celsius to Fahrenheit, right? So we use Fahrenheit, but everybody else is using Celsius. So if I have Fahrenheit, I have to convert to Celsius. If I have Celsius, I have to convert to Fahrenheit. So we are deriving that formula. If you don't like the fraction, it's 1.8. So you want to know this formula, okay? You want to just know it. Now, we're going to treat the numbers in the formula as exact. So we will never use these numbers for significant figures. We're going to treat them as exact. If I need to rearrange this to convert from Fahrenheit to Celsius, well, how do I do that? I'm going to subtract 32 from both sides. Really, I should have just went minus 32 here, minus 32 here. This cancels. And then when that cancels, I'm left with 1.8 times my Celsius temperature, because again, Fahrenheit moves more rapidly, and then TF minus 32. So how do I get the Celsius by itself? Divide both sides by 1.8. And that would be my way to rearrange it. So you should be comfortable algebraically rearranging this formula to this formula. Now, a lot of people are like, I don't want to memorize a bunch of formulas. Don't. Memorize one and then convert to the other one using algebra. Now there is one more, because there's the absolute temperature scale. When we get to the gas laws, we'll be using this. So the absolute temperature scale, okay, is, and the coldest possible temperature would be absolute 0, but that doesn't happen because virtually every motion would stop. So even a solid has vibrational energy and movement within the atom, because the electrons are moving, the protons are spinning on their axis. So this is like a theoretical absolute. You can't reach it, okay? You can extrapolate it through experimentation, and I'll get more into that when we get to the gas laws. But essentially, we said that the change was the same, the slope change. But the difference is, if we make an absolute temperature scale 0 Kelvin, it ends up being the same value as a negative 273.15 degrees Celsius. So to get Kelvin, you add the two, and really I should put 273.15. In this class, I'm a little more lenient, but you would add to whatever degree Celsius you have 273.15. So what does that mean? Well, if I'm at negative 273.15, which is absolute 0, and I add 273.15, that would give me the absolute 0 Kelvin. And it's a way to start the scale at 0. I'm basically just taking the temperature, and instead of having, you know, the absolute point be negative 273.15, I'm just adding 273.15. So now on the number line, I can start at 0. It's basically, I'm just moving it over, giving it a new, right? Because remember, I said they had the same slope. Just giving it a new y-intercept, a new starting point. Okay. What's kind of important is, you know, I don't expect you to memorize, you know, the temperature of the sun, but you should be comfortable with room temperature and when water freezes. So, you know, room temperature for Fahrenheit is about 70, roughly 70 degrees. Water freezes at 32. But for Celsius, 0 degrees Celsius. And you're talking about 20 to 25 degrees Celsius for room temp. And then we have, you know, the Kelvin scale. So remember, we're adding 273, right, for our Celsius to get the Kelvin. Okay. All right, so 0 Kelvin, negative 273. So let's work on a problem, right? So the pepperoni pizza that I had in the picture, right, that was frozen, and I had to add heat to it to warm it up so I can eat it, right, is baked at 45 degrees Fahrenheit. What is that in Kelvin? So I have to think to myself, all right, do I remember the Kelvin formula? Yeah, Kelvin was degrees Celsius plus 273. And I'll add the 1.5. You don't really need to for this class, but I'll put it there. The problem is I don't really have Celsius to solve for Kelvin. I have Fahrenheit, but I do know that Fahrenheit was the 1.8 degrees Celsius plus 32. So what can I do? Well, I have 455 degree Fahrenheit equals 1.8 degrees Celsius plus 32. So I'm going to subtract 32 from both sides. And I get 423 degree Fahrenheit equals 1.8 degree Celsius. And now to get the Celsius, I divide both sides by 1.8. And my degree Celsius becomes, what's that? 235. And I'm not using the 1.8 and the 332 for significant figures, right? So when I did this subtraction here, I used the original 455, which is at the ones place. So my final answer had to be at the ones place, which is 423. When I divided by the 1.8, I'm not using the 1.8 and saying, you know, it's 2 sig figs. I'm using the 423. It should be 3 sig figs. And I'll repeat that because that's a little tricky because I'm actually using two different rules. I'm using the addition subtraction rule, and then I'm using the multiplication division rule. For the addition subtraction rule, remember, I'm subtracting 32 from both sides, okay? Using that rule, I use the precision, the least precise measurement. That precision is based on the ones. So my answer should be to the ones. That's why I had 423. Based on multiplication division, I picked the fewest sig figs, significant figures. So some people might say, well, there's 2 here, there's 3, I should have 2. But I'm treating the 1.8 as an exact number and I'm not using sig figs. So I look at the initial temperature of the 3. So my final answer here has 3. And now for Kelvin, what do? I add 235 plus 273.15, but I'm not using the 0.5, and I'll kind of erase this because it's part of the formula and I'm treating that as exact. So if I was to add this, I'm not using this number anyways, right? I'm not using this because I'm treating it as exact. It has infinite sig figs. I'm using this number. When I use this number, I go to the ones place. That's the precision. So my final answer, if I was to add this up, right? If I put this on a calculator, it's 508.15, but I can only go to the ones place. So my final answer is 508 Kelvin to the ones place, which leaves me with 3 sig figs. Okay, but you do want to follow those rules because I know here you have 3 sig figs, but you might not always end up with the same number of sig figs. That's why you want to kind of follow those rules. So at this point, we talked a little bit about the conservation of mass. We can't create or destroy it. Then we talked about the conservation of energy, right? We can't create or destroy energy. We can merely transform it. We talked about how kinetic energy is associated with movement. Potential energy is associated with position. Really, in terms of this class for chem, the kinetic energy is really heat energy, thermal energy, because as particles move faster, they have more energy. Movement, kinetic energy. And they can transfer that thermal energy based off collisions, like we had said earlier when we were talking about changing potential energy to kinetic energy. The potential energy is really, you can think of as based on position, and the nucleus that has a positive charge is attracted to the electrons that are outside of the nucleus. And based on the position of those electrons to the nucleus, that gives stored potential energy. So when we talk about the bonds, which are formed by sharing electrons, that's a form of potential energy. Then we talked about the units of energy and how we can go from joules to calories. And then we talked about how the dietic calorie is basically 1,000 calories or a kilocalorie. And we talked about how with temperature, really what we're doing is we're measuring the current state of an object's thermal energy. We're not measuring the transfer of the thermal energy like we do when we do heat calculations and get units of joules and calories. Temperature is a different unit because it's not a transfer of energy. It's just saying at that state, what energy does it have? But the last thing I need to discuss in this lecture is what's called a change of state. Change of state is when I go from one state to another. So the melting point, and for water, that's like the one melting point you should know. The melting point from water is 0 degrees Celsius. So what that means is for me to melt, to go from an ice cube that's solid, that has a fixed structure, for it to melt, it becomes a liquid, okay? Now to do that, what's odd is I'm gonna add heat energy, but the temperature of the solid and the liquid doesn't really change until everything's converted to a liquid. Because that heat now, what it does is, it doesn't cause these particles to really move faster, it just separates them. So they're not moving faster, it's just creating a greater distance. The reason why that's important is now that there's a greater distance, they're not as sticky and they can move, and that's why they're a liquid. So melting point is from a solid to a liquid, freezing is the opposite, okay? And if I go from a liquid to a solid, heat would actually be released instead of absorbed, right? So to melt something, heat has to come in, so that is a positive. If I'm freezing something, the heat is being lost, so if I lose something, that is negative, okay? So, and I just said that, it's the reverse. We also have boiling, right? So if I'm a liquid and I want to boil and become a gas, I put heat, but again, initially, when I put the heat in, it doesn't change the temperature, it changes the state. And how is it that it doesn't change temperature? It just takes the particles, moves them further apart, so they're still, you know, their motion's not necessarily different. It's just creating more potential energy. So now the heat isn't used for kinetic energy, it's used for changing the position of the particles, potential energy. And now, because they're further apart, they don't stick. And later, if I keep adding heat, they can start moving faster. But initially, that energy is to separate them, okay? To boil water, it's obvious, you have to put heat in. The opposite of boiling or vaporization, the reason why it's called vaporization is the liquid's becoming a gaseous vapor, is condensation. So you see this, you know, you have a cold can of, you know, soda, there's water vapor in the air, it's a gas. When it hits that can, right now it loses some of its kinetic energy. When it loses its kinetic energy, it's moving slower. And now what happens is it's transferred the kinetic energy to the can so that it vibrates more. But when it moves slower, now the molecule starts sticking and you get a liquid. So at the same temperature, a gas can be converted to a liquid if you remove the heat, right? A liquid can be converted to a gas at the same temperature if you add heat. So that's tricky for people. So to help understand that, we use what are called heating curves, and the curves help us understand it a little bit better. So the changes in temperature, right, are typically positive slopes when we heat things. And then when the physical state changes, so I don't have a change in temperature, I just go from, let's say, solid to liquid or liquid to gas, I have what's called a flat curve because there's no change in temperature. So on the heating curve, right, the horizontal lines represent a phase change and the diagonals show an increase in temperature, okay? So the melting point of water is 0 degrees Celsius. The boiling point is 100 degrees Celsius. I could have ice, so this would be ice. We'll just say ice water. Let's say negative 10 degrees. So initially when I heat it up, right, there's no change in the position, in the potential energy, but now the molecules are vibrating. It gets to the point where the structure kind of is disrupted, and now the particles are further apart. When I'm moving them apart is where I get here. That's when I'm melting it. So now I'm putting heat in the system, but instead of having it vibrate faster, now that heat just separates them. And it'll keep doing that until all of it's a liquid. Now, when all the particles are no longer in that fixed structure and they're a liquid and they're free to move, if I keep putting heat in, now they're going to move faster in that slipping and sliding mode. And then I'd have the temperature increase in liquid because I could have higher temperatures of water. Eventually, I'll get to where it'll boil. And then at that point, it'll plateau again because now I'm separating the liquid so that it's further apart until eventually it'll get far enough to be considered a gas state of matter. And then if I keep heating it, now the gases will move faster. Instead of the energy being used to separate it, now they're going to move faster and their temperature will increase because I could have steam at like 110 degrees Celsius. The opposite of a heating curve is a cooling curve. So that's where, instead of boiling, I would call this condensation. So I would be losing heat, right? Because now if I'm steaming, I'm moving fast. And then I slow down and I get closer and I start sticking into a liquid. I lost some of that heat. And then I keep sticking until it's all a liquid. And then the liquid water can keep losing heat and get colder and colder to where now it's moving so slow that now it starts sticking and becoming a solid. And eventually it'll all freeze. And then once it freezes, once it's stuck in its lattice structure, you can even take more energy out so the vibrational energy slows down. So again, horizontal phase change, diagonal temperature change. In this class, we don't do heating curve calculations. In other chemistry courses, right, you actually do. There's an enthalpy of vaporization. There's an enthalpy of fusion, and we can do those calculations. For this particular course, we're not doing that. I'm just talking about it conceptually. And that's for the most part. We will be doing the calculations of converting units of heat from calorie to joules, also the temperature calculations. But there is one more state change, and people don't always think about this because it's not always obvious. We think solid, liquid, gas, it's a normal progression. But there are some substances that go straight from a solid to a gas, and that's referred to as sublimation. An example of that, CO2, dry ice. It's really cool stuff. You can get it at like ice cream shops, but you can take a piece of dry ice, put it on the ground, and you'll see it sublimate and go straight into a vapor. In fact, it's really neat at Halloween. You could throw it in your, witch's brew. Well, my wife and I used to do that for the kids. We get a big, what are those called? Not a trough, but a big witch's pot, put punch and throw the dry ice and it would bubble up, and the kids thought it was so neat. But basically, from solid to gas is sublimation. The opposite of that, and a lot of people have heard of sublimation, this is a tougher one. It's deposition, right? Deposition is where I go from a gas to a solid. And this is how you get freezer burn in your food. So, you know how people talk about freezer burn? Well, in your freezer, there's water vapor. And when it freezes and deposits into a solid, then you get all that ice on your food. And it's, whoops, what happened there? Sorry about that. So that's an example of freezer burn, where you get that ice depositing onto your food from the water vapor. When you open the freezer, goes in there, it's in a vapor stage, and then you close it. So just the main thing for this class, we're not doing calculations. What we're trying to do is to understand if I go from a solid to a gas in this direction, it's called sublimation. If I go from a gas, freezer burn, to a solid, that's deposition. More people are more comfortable with going from a solid to a liquid. That's melting. The reverse would be freezing. And then liquid to gas, it's evaporation. They call it vaporization, but really we could say boiling. And then this is condensation. So that is chapter 3, lecture 2, where we're discussing, we started with matter. Now we're discussing the different forms of energy. And the last lecture for chapter 3 will be focusing on, okay, now let's do some energy transfer calculations. Let's do some thermal energy calculations with the units of joules. And that's what we'll be doing next. And the topic will be specific heat of substances, which is the ability for a substance to absorb energy without changing temperature. So that'll be the next lecture. I want to thank you guys for watching. Let me know if you have any questions. Thanks so much.